All right, let's go on to our next speaker, who will be Subhankar Ghosh from the University of Minnesota. And their talk will be Reducing Sea Level Rise Prediction Uncertainty, a Spatial Variability Aware Approach.
Good morning, I'm Subhankar. I'm a PhD student in computer science at the University of Minnesota. And I'm here to present our work on reducing sea level rise prediction uncertainty, spatial variability, on behalf of my collaborators Shuai, Jayant, Arun, and my advisor, Professor Shashi, Shekhar, and Professor Aneesh Subramanian. Here is an outline of our talk. So first I'll be covering the motivation, the background, the problem definition, some of the challenges, and the related work limitations. Our contribution, then our proposed approach, our validation, and then I'll conclude with our future work. For the motivation, sea level rise is one of the most important and very challenging problems in climate science today. The IPCC, which is the Intergovernmental Panel on Climate Change, forecasts that the sea level will rise by around 0.26 to 0.82 meters by 2100. And this is an estimate of the global sea level rise, which is the global mean sea level rise throughout the Earth. But regional factors such as tsunamis or tides can also have a differential impact at different regions. So for example, I think like the previous speaker was talking about the Chesapeake Bay near Maryland, the forecast over there is around 0.3 meters to 0.5 meters by 2050. Now, most of the previous research works that have been done in modeling in the prediction of the sea level rise has mostly been on like selecting subsets of projection models to perform the forecasting. And also like after that, some of the more comparatively previous works or more recent works have been done on uniform averaging of the different projection models to perform the future predictions. But the problem with that is that a uniform averaging or a uniform weighing scheme might do well in certain regions, but not in every region because it's not spatially aware. Now, a spatially aware model, such as a spatially variable weighing scheme, would perform a differential weighing such that the models which perform better in certain regions are assigned more weights compared to models which don't do well in that specific region. So we are trying to perform a differential weighing of the projection models across the different regions. For some of the background, so if you see at figure 1, I think it just shows the interaction of the dynamics between the ocean, the sea, and also the atmosphere. Because there are different factors which contribute to the sea level. So for instance, the ocean dynamics can bring the warm water in close proximity with the ice sheets, and that can lead to the melting of the ice sheets. Atmospheric temperature changes can also have an effect on the surface of the oceans, which can also further lead to ice sheet melts. Now, this reduction in the ice sheet or the ice mass balance can introduce more water volume into the oceans. And this can have an effect on the sea level. Now, the regional factors, which are tsunamis or tides or boundary waves, these don't actually affect the sea level uniformly across the globe, but this can lead to a sea level rise or a sea level fall at different regions where we find such factors. Now, if you look at figure 2, this shows the contribution of factors such as the ocean mass balance or thermal expansion on the global mean sea level. So we can see that the green plot over there that shows that it has a much higher effect on the global mean sea level than the thermal expansion. Now, if you ask, like, how are these measured? So the global ocean mass is actually measured via satellites such as the GRACE, while the thermal expansion is measured by Argo floats, which are free drifting floats, and they actually measure the heat content of the oceans, and there are close to 4,000 such free drifting floats. And these Argo floats actually measure the temperature and the salinity changes in the ocean as well. So to conclude, in this specific slide, we can say that the ice mass balance has, the ocean mass balance has a significantly more impact than the thermal expansion on the global mean sea level. For the problem definition, we are performing a data-driven approach. We have the observed or the ground truth data of the sea level, and this can be obtained from organizations such as Copernicus, which provide us the satellite data as well. So it's basically the ground truth or the observation of the sea level across the Earth. We also have projections, that is the simulated projections, which incorporate the physics as well as the underlying dynamics. And these are CMIP6 models that can be obtained from organizations such as NCAR. Our output that we are trying to obtain is a multimodal ensemble, which comprises of differential weighing of these simulated projections. And it is a convex combination, so it's just, we are trying to weigh the models, that is the simulation, such that we are assigning greater weight to the to the models which have a higher prediction capability in that specific region are. And our objective is to improve the prediction accuracy as well as reduce the uncertainty of the prediction. For our constraints, the spatial variability mostly can lead to a heterogeneous weighing scheme. So it's just that you cannot have the same sets of weights across every region. And you want to have a specific set of weight to the region that you're looking at. Some of the challenges and related work limitations. The previous works that have been done, they focused more on either picking subsets of the projections or the simulated projections that were doing better in the forecasting step. And also some of them also focused on equally weighing or like equally or assigning equal weights to the different projection models and perform the averaging. Now, the issue with such models is that different simulations might incorporate different physics and different underlying dynamics. So if you leave out a few of those models, it is possible that you're not including some of the physics or some of the underlying dynamics that are being considered by some of these organizations which perform these simulations. So it is important that we perform a differential weighing of these different simulations so that even if you're looking at a specific region, you're considering all the different physics and maybe you're assigning greater weight to a physical factor or underlying dynamics at that specific region, which is more essential. This spatial variability also leads to heterogeneous weighing scheme, as I mentioned. And another challenge of this specific problem is the interdependency between the models. So if you look at different forecasting models, many of them might incorporate similar physics or similar underlying dynamics. And if some of these models or a few of these models are doing the prediction incorrectly, that can lead to a bias in the projections. And this bias can also lead to a greater or worse prediction accuracy in terms of the forecasting. So for our contribution claim, we are proposing a zonal regression approach, which tries to incorporate the spatial variability. And basically, we are trying to assign higher weightage to a model which does better prediction at that specific region instead of considering the global performance of the different models. And we also performed comparative analysis, which shows that proposed approach can do more reliable projections. We are doing a zonal regression, which addresses spatial variability, but we can also formulate this as a least square problem, where we are trying to minimize the difference between the observations that we have, and we can, as I mentioned, we can get these observations or the ground truth from the Copernicus data set. But we are trying to minimize the ground truth with the convex combination of the weights that we obtain and also the simulated projections that are obtained from organizations like NCAR. And the weights are semi-positive, and since we are performing a convex combination, we want to ensure that the weights add up to 1. The resultant weights are not uniform. We are not doing a uniform averaging, but we are looking at a differential weighing so that if you look at the weights that is WRI at the specific region R, we want to assign a greater weight to the region, to the model which performs better at region R in terms of forecasting. For our experimental evaluation, we want to compare the prediction accuracy of our proposed approach with the baseline approach and also the individual simulation models. We also want to compare the prediction uncertainty of the proposed approach with the individual simulation projections as well as the baseline approach. For our experiment design, we have the two data sources that are the simulated projections as well as the ground truth data. And methods, I think, if you look at the baseline approach, those are two papers which are very commonly used in the climate domain, which are papers by Sanderson at NCAR. And they mostly use a global model to perform projections across the globe, like at every region around the world, instead of considering the spatial variability across different regions. And then we have our proposed approach where we are doing the zonal regression. And we mostly use the root mean square error to perform our experiments. Yeah. So these are preliminary results, and right now we are mostly focusing on the Eastern North America region, that is the coastal region. And we see that our proposed approach has an RMSE of 0.35, while the baseline has somewhat close to 0.36. Now, our proposed approach considers the spatial variability in terms of the weighing, while the baseline does not. It just considers the global weighing scheme of the different models. The individual projections, which might not consider the same physics, or different models might not consider the same physics or the dynamics, they usually have a greater error, which would be greater than 0.36. And in terms of the uncertainty, our proposed approach is somewhat close, but we are trying to still work on it and improve upon it in our future work. So if you look at the figure 4, the first few plots that I mentioned, the CSM2 and the CSM2FV2, those are different individual simulated projections from CMIP6 that we can obtain from NCAR. Then we have the proposed approach and the baseline approach. The outliers are mostly, which are just 1.5 times above the interquartile distance. For our conclusion, we have the proposed, we mentioned the proposed approach, which is the zonal regression model, which addresses spatial variability, and we performed a comparative analysis with our preliminary results. Yeah. For our future work, we plan to extend this to approaches that are beyond regression right now, and we want to work with physics-informed models such as GWR, like incorporate physics-informed models with GWR. Then we also want to work with spatial variability of our deep learning methods. And something that we are actively working on is to handle the interdependency between the models, which can lead to greater bias in terms of the projections. And also something that might be very interesting is to perform the predictions at a much higher resolution instead of what we have right now. We are thankful to NSF, to the Spatial Computing Group, Cayman, and NCAR for the data. Yeah. Thank you. Any questions?